So in today's lecture, we are going to consider valence bond theory of bonding, which is the second theory of bonding that we have looked at and that we'll be studying in this course. The very first theory was VSEPR, valence shell electron pair repulsion. That was done last lectures. And just to quick refresh your memory, we can understand these simply by first drawing Lewis dots, and then we're going to count the number of bonding pairs, lone pairs, the number of electron pairs, whether they're bonding or lone, bonding pairs or lone pairs, around the central atom. And we are still going to consider the exact same criteria in a new theory of bonding called valence bond. So we're still going to be first drawing Lewis dot structures and then counting the electron pairs around the central atom, and an electron pairs or electron groups, it's better. Groups of electrons, because if you have a single bond or a double bond, that's a group. That's considered a group. And valence shell electron pair repulsion simply said that each electron around the central atom, each negatively charged density around the central atom is very important, and they're going to repel each other. So we had said if we have two groups of electrons around the central atom, one would be pointing east, the other one would be repelling it, pointing west or north and south, opposite 180 degrees, and the shape, the electronic geometry would be what? Linear. Okay, so was the case for CO2. When we did BF3, we did Lewis for BF3. Now we ended up boron in the middle, fluorine, fluorine, fluorine. Three groups of electrons around the central atom. They repel each other, and they're going to be 120 degrees apart. So the shape would be what? The electronic geometry would be triangular or trigonal planar. If you have four groups around the central atom, like in the case of CH4, they repel each other. They're going to want to be 109.5 degrees, and the electronic geometry will be what? Tetrahedral. For a count of 5, it's trigonal pyramid. For a count of 6, was octahedral. Are we okay with that? Okay. So we are still talking about bonding, still talking about same theories that we were before, but we are going to be adding to the picture. Lewis dots is a very simple theory. Counting is the number of groups around the central atom, the central element, could determine the shape, the electronic geometry. But if we stop and think about, for example, CH4. This, I believe, it was our very first Lewis dot structure a couple weeks ago. Let's go back and do Lewis dot structure for CH4. And when I say CH4, it could be CCl4, CF4, any halogen could replace the H, right? So let's go back to CH4 and do Lewis. How quickly can we do that? Put carbon in the middle, and then what? 4 hydrogens around it. How many electrons is hydrogen bringing? 1, so we share it, and okay, so hydrogen is in the periodic chart is element number 1, only has 1 dot, 1 valence electron. It will be sharing it. So whether we have a hydrogen or a fluorine or a chlorine, you only share 1. And then carbon brings how many? 4. So you complete your octet for carbon, the 4 that it has, and 1 from each hydrogen. So you have How many covalent bonds? 4 covalent bonds. And we said it is not flat like the screen indicates. It's what? Tetrahedral. So these two are pointing back. And this one is forward. And the angles in here were 109.5. Yes, we remember all this good stuff? Okay, so the electronic geometry is tetrahedral. The molecular geometry is tetrahedral. Now let's think for a minute of what we're saying. What is the electronic configuration of carbon? Element carbon. 1s2, what else? 2s2. 2p what? 2p what? 2p2. I heard 2p6. Okay. And if we do arrows, it's 1s with 2, 2s with 2, and the 2 p's are 3 degenerate, px, py, pz, and we have 2 electrons there. Okay, then we have 4 hydrogens, and each hydrogen is a 1s1, correct? So you have a 1s with 1 electron. Now look at what we're saying. We have 1 carbon and 4 hydrogens. Let's think about what we just did. If this is the electronic geometry of the central atom, and these are the only 2 unpaired electrons, does it make sense if I have 2 unpaired electrons that I'm going to be able to accommodate 4 carbons? It doesn't add up, does it? 1 carbon could maybe bond to a hydrogen there, and the second carbon could bond to another hydrogen there, but what do we do here? A hydrogen bonding to a hydrogen? This, when we stop and think about what we did, doesn't make sense. Besides, the angles between the px, the py, and the pz are what? What are the 3 angles? The angles there. Px, py, and pz are what? They're 90 degrees, yes. And the angles here are what? Not 90 degrees. So when we stop and think about valence shell electron pair repulsion, there are holes in there. Actually, there's a piece of Swiss cheese. That's how many holes there are. This theory doesn't take you where you really need to go. So we are now going to consider another theory, valence bond. And in a nutshell, valence bond is going to assume that the covalent bonds are formed, thank you, when the atomic orbitals of the different atoms overlap. But sometimes this works. Like if I have H2, yeah, well, H can combine with another H, and the other H is also going to be 1s1, so 1H and the other H brings this, so when you form H2, you have 1H up and 1H down. That's a bond between an H and an H. That's fine. But if you try to explain CH4, then it doesn't work. How do you explain 4 hydrogens overlapping their atomic orbitals with a carbon if the electronic configuration of carbon in the valence shell is an H2sp2? Okay, so we are going to discuss another theory that will take another point of view, another series of variables considered, called valence bond. And what valence bond does to explain the formation of CH4, C is the central atom, is the central element. And I am trying to explain how come I have 4 bonds in CH4. How come those bonds are 109.5, which is what spectroscopy tells us. So valence bond says, okay, carbon has a valence configuration of an S2P2, right? It's 2s2, 2p2. If it would have been silicon, it would be 3s2, 3p2. If it would have been germanium, it would have been 4s2, 4p2. But anyways, it's an S2p2 because it's an element in group 4. Okay, so in the case of carbon, it's 2s2, 2p2. So we're looking at the valence shell for the central element, the one that's directing the shape. And then it says, well, the s orbital is spherical. The p orbitals are dumbbell-shaped, 90 degrees along the x, y, and z axis. And if I take the equation, the mathematical equation that corresponds to the s orbital, and take the 3 p orbitals, and I combine those equations, I take an average. So I'm taking one s orbital, the 2s, specifically for carbon, and all 3 of the p's. What's 1 plus 3, guys? 4. So 1 plus 3 is going to give me 4 new hybrid orbitals. There are no longer going to be s's, spherical. They are no longer going to be p's along the x-axis or y-axis or z-axis. They are going to be new orbitals, and they're going to have a new name, and there are going to be 4 of them. And since I took 1s and 3 p's, the 4 new orbitals are going to be called sp3s. So I'm going to have an sp3 and another sp3 and a third sp3 and a fourth sp3. And these orbitals are neither spherical nor dome-shaped shape. They are going to be pointing towards the vertex of a tetrahedron. So that's an sp3, that's another sp3, that's another sp3, and that's another sp3, which are going to be pointing towards the vertex of a tetrahedron. Let's see what carbon would do. If I take my, I'm going to rewrite this because it's a little high, 2s2, 2p2. Okay, so I have 2s with 2 electrons and my 2 p's with 2 more. And I am going to combine these, and I'm going to make 4 new orbitals, and each one of these is an sp3 orbital. Okay, so I combine 1s with all 3 of the p, the px, the py, and the pz, all 3 of the p, and I form 4 new orbitals. How many electrons did carbon have? 2 in the 2s and 2 in the 2p, so I still have 1, 2, 3, 4 electrons in my central atom. And they're no longer s's, they're no longer p's, they're new hybrid orbitals. Now my hydrogen, which is a 1s1, could come in here and pair up, and my second hydrogen can pair up, and my third hydrogen can pair up, and my fourth hydrogen can pair up. You can put the arrow up, or you can put the arrow down. Doesn't matter. If your carbons have the arrows up, then your hydrogens are going to have it down. If your carbons have the arrow down, they're spinning clockwise or counterclockwise. It doesn't matter which one does which. Okay, so now you have your 4 hydrogens here, and these are atomic. These did not create a new hybrid orbital. These are atomic s's from the H, from the hydrogen, overlapping with each one of the 4 sp3s of the carbon. So if we go back to our original chart and we try to explain CH4, this right here, and now we say, yes, we have a count of 4. We have 4 groups of electrons around the central atom. That's what Lewis told us, and that is what valence bond theory of hybrid orbitals is also telling me. For a count of 4, my hybrid orbitals are sp3s, and I have 4 of them. This is number 1, number 2, number 3, and number 4. And they're pointing towards the vertex of a tetrahedron, just like we said before, but it's explained totally different. In CH4 is an sp3 of carbon bonded to an 1s of hydrogen, and the second hydrogen, and the third hydrogen, and the fourth hydrogen bond together. So once you have that, you're going to have an electron of hydrogen and an electron of carbon pairing up, and those are my 4 bonds. Okay, so bottom line, for a count of 4, which is what Lewis told us you had, count of 4, you combine 1s and 3 p's. The p, x, p, y, p, c, those are 3 p's. Gives you 4 sp3s. Are we okay with what I just said? So we're getting to the same place, but not in the same fashion. What would happen if I have a compound like pH5? How do I explain the bonding for pH5? What's valence bond rendition? Okay, so again, I start with my electronic configuration for the elements comprising this compound, and phosphorus is what? Valence shell is 3s2, 3p3. And then I do the arrows, because I'm really saying that an electron pair is forming a bond and they're overlapping. So my 3s is going to have 2 electrons, and my 3p's are going to have how many? 1 in each. 1 in the px, 90 degrees apart from the py, 90 degrees apart from the pz. Now, does it make sense that 5 hydrogens are going to bond in there? If each hydrogen is bringing a 1s1, I can maybe put 1 hydrogen there, and another hydrogen there, and another hydrogen there. What do I do with hydrogen number 4 and hydrogen number 5? So the atomic orbitals do not explain the formation of molecules. Okay, atomic orbitals are good for elements, for atoms. But once you start to mingle your atoms, mingling these elements to forming compounds, and pH5 is a compound, atomic orbitals don't work. But valence bond comes to our rescue. How do I get to what valence bond has to tell me? I first do Lewis. So I still do the same thing. I still do Lewis, and I still count, just like I did last week. And then I see what valence bond has to offer. Okay, so when I do Lewis for pH5, P in the middle, 5 H's, anywhere you want. 1, 2, 3, 4, and 5. Hydrogen brings 1 dot, 1 electron, and phosphorus brings how many? 5. 1, 2, 3, 4, 5. Okay, so I'm doing Lewis. Nobody has a problem with Lewis, correct? And how many bonds do I have? 5 bonds. So I'm going to have P here, PCl5, pH5, PF5, they're all the same. pH5. I'm going to have my phosphorus in the middle, HHH. 1 H above the plane, 1 below, and 3 more in the triangle plane. Right? That's what I had last week for valence shell electron pair repulsion. Okay, so I am going to put my, this is last week, my H above, my H below, my H, my H, my H in the triangle, and I have a bond in each one of these. And the angles here are what? What were they? 120, because it's a triangle. And the angle here is what? 180. And the angle here between any one of these is, I'm sorry, between this and that, that's 90 degrees. Okay, so I have a count of 5. So I need 5 bonds. I did Lewis and my count was 5. What does valence bond says? Okay, valence bond says take the central atom, and this is your central atom, S2P3. 3s with 2 and 3p. In the third energy level, we have the 3s's, the 3p's, and what else do we have? The d's. And the d's are empty in the case of phosphorus, but they're there. Orbitals are region in space. Their regions are there. The space is there. They just happen to be empty. But in this particular case, we need to use them. Why do we need to use them? Because there's 5 hydrogens. Okay, if I had 3 hydrogens, Maybe. Even 3 hydrogens would not work because 3 hydrogens in pH 3, the angle is not 90 degrees, which is what the atomic orbitals would indicate. Okay? But in here, I need a count of 5. So I'm going to need to take the s orbital, that one right there, s. All 3 of the p's. The px, the py, and how many of the d's do I need? 1 plus 3 is what? 4, so I need what? 1 more of the d's. So I just take 1 d. So 1 plus 3 plus 1 gives me what? 5 new orbitals. And they're hybrid. Because they're no longer, it's like I put it in the blender. I put the s and the p and one of the d's in the blender. And I no longer have an s, spherical. I no longer have a p or a d. I have new orbitals, and they're going to be called what? sp3ds. And another sp3d. And a third sp3d. And a fourth sp3d. And a fifth sp3d. And how many electrons do I have in the central atom? So this is central atom. Central B element. I have 1, 2, 3, 4, 5. Okay, so I'm going to put my sp3d, second, third, fourth, fifth. Here, each one of these is an sp3d. And I am going to put my 5 electrons that the phosphorus is bringing. 1, 2, 3, 4, 5. These 5 new hybrid orbitals are pointing just like this is an sp3d, and that's an sp3d, and an sp3d, and an sp3d, and an sp3d. Pointing towards a vertex of a trigonal bipyramid. Okay, so I first learned VSEPR, valence shell electron pair repulsion. I first learned Lewis. I first count, and then I put it all together with valence bond. Okay, so I have how many hydrogens? I have 5 H's. And each one of these is going to be a 1s1. So I want to put my first hydrogen and my second and my third and my fourth and my fifth. So what am I saying? I'm saying that I have a trigonal bipyramid, but each one of these bonds between the phosphorus and my H and H and H and H and H, it's not an atomic B with an atomic S of the hydrogen and the phosphorus. That doesn't work. These guys combined, they form new orbitals. They're hybrid between an S and a P and a D. And if I combine one S and 3 B's and 1 D, I have a total of 5 new orbitals. Okay, so each one of these is a bond, and each one of these is an sp3d of hydrogen phosphorus overlapping with the S. Okay, these are all sigma bonds. So I have 5 sigma bonds, very strong overlap, head to head. And each one of them is an sp3d of phosphorus overlapping with a 1s of hydrogen. So that's an sp3ds, another one, and I have 5 of them. Are you okay with me so far? Okay, let's try to do sigma as opposed to pi. In a minute we're going to have double bonds. Okay, so when you have a double bond, you always have to have a sigma. Sigma bond is a very strong head-to-head overlap. Okay, so if you collide with another car head-to-head, that's a very, very strong collision. As opposed to side-to-side. Pi bonds, when you have double and triple bonds, you always have to have a sigma. Otherwise you won't have a bond. That sticks, that stays. But the second bond in a pi bond, when you have a double bond, or second and third when you have a triple bond, those are pi bonds. Okay, so we'll talk about more on sigma. Sigma is a very strong head-to-head overlap between the two orbitals. Boom, they collide. And they form that covalent bond. Okay. Let's do SH6. And HX6 would be the same as who? As S what? F6. The same as what? SCl6. SBr6. S. All these guys, the halogens and hydrogens will share one. Right? So Lewis is not changing on us. And we're still going to do Lewis. We're still going to count. And then we see the valence bond rendition of this molecule. Okay, let's consider what's the first thing. Valence shell of sulfur. My central atom. Okay, so I look at my central atom, and in this case, my central element is sulfur. What is it? 3s2 and 3p4. Okay, so hopefully electronic configuration is not a big deal. Yes, that's totally learned. And hopefully Lewis is not a big deal either. Now, does this make sense? If sulfur has an S2p4 and 2 unpaired electrons, and I'm going to be able to handle in there, form 6 bonds with H, or with fluorine, or with chlorine, or with another element? I don't think so. I would maybe pair one there and one there, but I don't know where the other ones would go. Okay, so atomic orbitals are not explaining it, are not cutting it. I need to bond, and let's do Lewis first. I need to bond to 6 hydrogens. So let's do Lewis. Hydrogen and hydrogen and hydrogen and hydrogen and hydrogen and hydrogen. And whether it's hydrogen or fluorine or chlorine, they share what? 1. And sulfur has 6, 1 for each. 1, 2, 3, 4, 5, 6. And then when I did Lewis, I say, okay, I have a bond up, a bond down, and then on the plane, I have 4 more bonds. And I'm going to have my fluorines at each end, or my chlorines, or my hydrogens. I just put hydrogens for simplicity. They didn't need to be hydrogens. So I have a total of 6 bonds in SH6. Okay, so I'm doing this for homework, do these other guys. Same thing. Now, what do? The 3 Ds are empty, but they're there. After period 3, sulfur, phosphorus, these elements are all period 3. We have the 3D orbitals available. I take the 1s, one of the s, this one right here. All 3 of the p's, the px, the py, and the pz. 1 plus 3 is 4. How many more do I need? So now I need 2 of the d's. 1 plus 3 plus 2 gives me a total of 6 new orbitals. So what are my hybrid orbitals? sp3d2, also called d2sp3. By the same token, sp3d are also called dsp3s. Okay, 1d, 1s, and 3 b's gives me 5. Now I have 1s, 3 b's, and 2 d's. That gives me 6. Okay, so now I have my s with 2, my p for sulfur is p4. Okay, so I have S2P4. I'll rewrite it. 1, 2, 3, 4. This is atomic. Atomic for my sulfur. Atomic orbitals. and the D's were empty. And now I take this guy, all three of these guys, and two of these guys. So I'm making 6 new hybrid orbitals. And each one of these is no longer an S, it's no longer a P, it's no longer a D. They're no longer atomic. They're no longer bachelors. These are sp3 D2. And another sp3 D2. Do we understand? Why do we have 6? Okay, so 1 S, 3 P's, and 2 D's give me 6. sp3d2, 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 1, 2, 3, 4, 5, one more, sp3d2. So I have 1, 2, 3, 4, 5, and 6. And I have my 6 electrons from sulfur. 1, 2, 3, 4, 5, 6. There, pointing towards the vertex of an octahedron. Okay, and then my 6 hydrogens, hydrogen atomic orbitals, they don't change. The 1 is 1, 1 goes there, 2, 3, 4, 5, 6. If I had fluorine, fluorine would have been an S2P5. Okay, so fluorine would have had 1P, S2. Fluorine, chlorine, bromine, iodine, they're all going to have a P. 1, 2, 3, 4, 5. And it would be that guy, atomic P, that overlaps instead of the atomic S from the hydrogen that overlaps. Okay, so I am going to have my octahedron, my sulfur in the middle, and this is a D2sp3 or an sp3d overlapping with a hydrogen. Same thing here. Same thing in each one of these other ones. So I think by now we're getting the picture. So each one of these bonds is not an atomic S and an atomic H orbital. It's a hybrid orbital of S. Okay, so each one of those is an sp3d2 overlapping with an S. This is from your central atom, and this is from your hydrogen. Okay, so if you look at your chart, for a count of 6, SF6 or H6 or Cl6 will have 6, a count of 6, so you need 2 Ds, D2, 3 Bs, and 1 S. So that's 2 plus 1 plus 3 gives me 6. D2 sp3s. Okay, so bottom line, for a count of 6, what's valence bond's orbital? sp3d2. For a count of 5, what's valence bond orbital? sp3d. For a count of 4, what's sp3? So it's 1s and 3 p's. 1 plus 3 gives me 4 sp3s, count of 4. What about a count of 3? What would that be? 1s and, well, how many p's? P's are 3, but do I need all 3? No. If I only need 3 bonds, it's 1s and 2 of the p's. The px or the py or the pz or the px, it doesn't matter. 2 of the p's. What about a count of 2? Just 1s and 1 p, and we're done. Okay, so the same chart that we used last couple weeks to do Lewis and to determine the electronic and molecular geometries, we're just adding another column for valence bond. Okay, so no, I'm not going to give you this paper. You need to reason it out, and it's all very logical once you understand what's happening. Okay, so if I ask you what kind of, like in every question in the test, you're going to have maybe 5 molecules. I can give you this guy and this guy and this guy and this guy and that guy, and it's of these, which ones have an sp3d? So you need to do Lewis for each one of those 5 for every question. And the one that gets 5, which are these two, would be the sp3ds. Or I could have asked you for sp3 and then would have been this guy. Or sp3d2 and it would have been this guy. Okay, so do you see how many patterns? We're getting to the same place. We're getting to the same. Let's go ahead and answer your question. What's the deal with double and single bonds? Let's see, valence bond rendition for C2H4. What kind of valence bond? And I'm talking, is it an sp, or is it an sp2, or is it an sp3? I know it's 1s, 1p, it's 2 of these. 1s, 2p's, 3 of these, 4 of these, or is it a sp3d, or is it a sp3d2? These are the bonds we've seen. Okay, so the question will have this kind of lingo. But what's the very first thing we do? Lewis. And what's the next thing we do? We count. And we look at the central atom and we see how many bonding pairs, how many lone pairs that fellows in the middle have. And then we determine what valence bond hybrid orbitals would be. Okay, so it's going to be one of these guys. Either an sp or sp3s or... Okay, so Lewis, I'm going to assume we know how to do Lewis because we've done Lewis many times. So I'm going to go ahead and do Lewis for you. And hydrogen shares 1 because it's the only thing it has. Okay, and if it would have been 4 fluorines, it's the same thing, shares 1. And then carbon has how many? 4. So I'm just going to go like this, like this, like this, like this, like this, like this. These are my 4 of this carbon. This is my 4 of my other carbon. So I'm going to have a what? A double bond, a single, a single, a single, and a single. Okay, so I'm assuming we know how to do Lewis. It may take you more than 2 seconds. It took me just 2 seconds to draw it. But maybe it takes you 3 seconds instead of 4. And we go, okay, let's consider him as the center. How many groups of electrons does this fellow have? You have one group bonding to here. That's a cloud of electrons. A second one here. And a third one here. What about him? How many groups does this guy? Same thing. 1, 2, 3. So whether it's a single bond or a double, it's an electron negatively charged region. Electron density that repels each other. So this is going to have a count of what? Count of 3, and this is going to have a count of 3. For a count of 3, there you go, sp2. Okay, so you go back to your chart, which by now should be in your head. A count of 3. What we got for BF3 or for carbonate. Carbonate, you had a double, a single, single. Or SO2, which was a V shape. We're all count of 3. 1s, 2p's. S, S, and 2p's gives you 3 sp2s. So let's see how carbon is going to get to an sp2. Okay, and listen up because this is getting a little bit more complicated. Okay, so I'm now looking at the central atom. I'm going to call carbon number 1 and carbon number 2. They're identical. So whatever happens to the first one will repeat in the second one. Carbon number 1, atomic. Atomic orbitals for central element carbon 1. And it's going to mimic for carbon 2. So whatever I say for carbon 1 is going to repeat for carbon 2. What is it? What's carbon's element carbon atomic orbital? S what? S2P what? P2. Okay, and this other carbon is also an S2P2. 2S2 P2. Okay, so this other carbon is also going to do an S2P2. Okay, and this, actually let's put these guys down. So if one's spinning clockwise, the other one would be counterclockwise. Doesn't matter which one. Okay, it's just a relative. They have to be opposite. Okay, so one of these bonds of one carbon is going to be with one of these. And these won't cut it. Because there is no way if a count of 3 is giving me a triangle, that's a triangle right there. The angles here are around 120 that these people, which are 90 degrees, are going to bond. Okay, so elemental carbon, atomic orbitals for carbon does not explain the bonding of acetylene, of ethene. So I'm going to take these and I'm going to excite them, and I am going to form new orbitals. For a count of 3, what was it? sp2. Okay, so I'm going to form, if I'm forming new hybrid orbitals, why did I know it was going to be sp2? Because 1 plus 2 is 3, and I had a count of, okay, so I did Lewis and I counted, and my count was 3. 1, 2, 3 bonds around the central atom. And for a count of 3 is sp2s, 3 of them. And of the 3 sp2s, 2 of them are going to be bonded to hydrogens. Okay, so that's going to be an sp2 of carbon and an S of hydrogen. That's going to be a sigma sp2 of hydrogen and an S of hydrogen. Okay, so sp2 of carbon, so that is an sp2 of carbon overlapping with an S of hydrogen. So is that one. That one right there is an sp2 of carbon overlapping with an S of hydrogen, atomic S. Okay, and these guys are the same, and these two are the same. That one right there, sp2 and S. But what about this little fellow in the middle? Let's try to understand all the bonding. Okay, so I am going to form, okay, in reality I skipped one step. In reality, before we formed this, we excited and we put 1s, and okay, so this is really an excited state, and then we go ahead and hybridize the S and the P's. We take the 1s and these two. Okay, so this is an excited state, and we're taking an sp2, another sp2, and an sp2, and I have a leftover atomic P. And the same thing for the other carbon. The other carbon is, once I excite them, I put an S, and these are 90 degrees because they're P's, atomic PX, PY, PZ. I'm going to have to take the S and 2 of the P's. I take these, and I'm going to have a leftover P. Are we okay so far? Did I lose anybody? Are you with me? Okay, so to take sp2s, I'm taking this guy, and this guy. Those are my sp2s, and this is my sp2s. This is another sp2, sp2, sp2 of carbon number 2. And each one of them has an atomic P left over. Atomic P. Okay. So my carbon has 1, 2, 3 electrons. 1, 2, 3 electrons there. And this carbon number 2 is going to have 1, 2, 3 electrons. And then my hydrogen, which was in red, well, it's hydrogen, just 1s, 1s1. So I just put a hydrogen here in carbon 1 and another hydrogen in carbon 1. Okay, so these are, my first hydrogen is there and my second hydrogen is there, overlapping the sp2 of carbon and the S. And the other 2 hydrogens for carbon 2 is going to do the same. 1 hydrogen there, and hydrogen was red, so let's keep it red. And another hydrogen is there. But each carbon has a leftover sp2 and another sp2 that are unpaired. And this was up and this was down. So this overlapping, okay, so I'm going back to drawing my structure. Imagine a triangle, and when you have a triangle, you're going to have an H, an H, another H, and another H, and this is my other triangle. And these angles here are close to 120. So this bond there is an sp2 of carbon overlapping with an S of hydrogen. This right here, same thing, sp2s, sp2s. And this is an sp2 overlapping with another sp2 of carbon. Okay, so that's right there is my sigma bond. That's an sp2 of the first carbon and an sp2 of the second carbon. But each carbon has a leftover atomic p orbital. So this carbon has a, I'm going to write it in green. This is an atomic, and this is an atomic. And that fellow has one electron, and that fellow has one electron. So now put both your right and left arms up. And if you have a p up and down, north and south atomic orbital with one electron and another one here, they are going to come together side to side. And that's your second bond. That's your pi bond. So this right here, with an atomic p orbital of each carbon, is going to trigger a pi bond. So when I put my Lewis dot and I put double bond, one's going to be a pi, and all the other ones are going to be sigma. Sigma, sigma. Single bonds are always sigma. And when you have a double, one sigma, one's pi. When you have a triple, one sigma, two are pi. And this is what it looks like. I have my carbon in the middle. Count of 3. Carbon bonding to H. Carbon bonding to H. Carbon bonding to the other carbon. Carbon bonding to H. Carbon bonding to H. Carbon bonding to the other carbon. So this is carbon 1, this is carbon 2, and this is an sp2 of this guy and an S of hydrogen. sp2 of carbon, S of hydrogen, sp2 hydrogen, sp2 overlapping with an atomic S. And that is an sp2 of this carbon and the other sp2 of the other carbon. And this is an atomic P and another atomic P. And this whole cloud, I have an electron floating around there. That's my pi bond. Okay, so this is what I try to draw on the screen. And your text does a much better rendition. Are we okay there? One more. Questions in there? Do for me C2H2. This is acetylene. This right here is ethene. No, when you take organic chemistry, you'll learn how to name those. You need to know the valence bond. Excuse me? I give you this compound. I will not call it acetylene or ethine. I will just call it C2H2. And I can ask you electronic geometry, molecular geometry, Lewis dot, valence bond. And this lecture we're talking about valence bond. What is the valence bond explanation? How is the bonding for C2H2? Okay, so what is the first thing you do? Lewis dot. And what is the second thing you do? You count. So step 1 and step 2 is not new. The only thing I'm adding is step 3, which is valence bond. How the heck did 2 carbons and 2 hydrogens bond together? How do we explain that? And I'll do Lewis for you. If I have 2 carbons and 2 hydrogens, hydrogens forms one bond no matter what other element is combining to. Another hydrogen, a fluorine, a carbon is always one bond. And carbon forms 4 bonds. And in this case, it's a single and a triple. So this is Lewis. It may take you a little bit of time to get there. Carbon has 4 dots. Hydrogen has 1 dot. And you do your Lewis. Okay, so you have, now if we look at this as a central atom, how many groups of electrons does this carbon 1 has? And it has 2 groups, one to the right, one to the left. I don't care if one's a single bond and the other one's a double or a triple, or it's a negatively charged group repelling another negatively charged. So my count is what? 2. Same thing here. Carbon 2 has one to the right, one to the left. I'm trying to explain these bonds because atomic orbitals do not cut it. Okay, so now I'm going to valence bond. And to do valence bond, I need to come up with new hybrid orbitals. For a count of 2, what were my hybrid orbitals? SPs. A count of 2. Like CO2 or like C2H2. My hybrid orbital is 1s, 1p. A count of 2 is sp. Okay, so I'm going to get there. But I first start with my atomic orbitals of carbon. Okay, so this is what carbon does. Carbon number 1, central atomic, is 1s2, 2s2, 2p2, right? Or valence. Okay, so I look at my valence for my central, and it's an s2 and a p what? 2. That's my ground state. Then I excite it. And I go, I move that one there. S dot, and that's still carbon. That's still carbon that hasn't combined with anybody. It's just carbon excited configuration. I promote an electron from the S into the PZ. Then I do my magic for valence bond. Valence bond come in. And what bond am I using again? SP. So I'm taking one of the S's and only one of the P's. Why SP? Because I need one S and one P. 1 plus 1 gives me 2 SPs. Okay, so that's an SP and that's an SP. I take the mathematical equation for the S and the mathematical equation for one of the 3 P's, and I take an average of those 2. And that gives me a new shape, a new orbital, a new hybrid orbital. And they still have my 2 electrons. These guys I haven't touched. These are atomic, not hybrid. These are atomic, BX, BY, BY, PZ. And my other carbon is doing the exact same thing. So my other carbon, this is carbon number 1, and carbon number 2 is doing the exact same thing because it also has a count of 2. So the other carbon, valence bond for the other carbon is still going to be sp and an sp and an electron and an electron, and each one of these still has an atomic P and an atomic P and an atomic P and an atomic P. So then I go, okay, I have how many hydrogens? I have a total of 2 hydrogens. Each one of the hydrogens is a 1s. 1. So I'm going to put 1 hydrogen there and another hydrogen where? In the other carbon. Okay, so I'm taking this bond right here. And I'm saying that that bond right here is an S of the hydrogen atomic, normal, spherical, like always, overlapping with an sp of this carbon. And the same thing here. So that bond right there is another sigma bond, very strong head-to-head collision of the spherical S bond of hydrogen and an sp. Okay, so these are all sigma bonds. And this one of the 3 is an sp of this carbon overlapping with another sp of that carbon. So carbon 1 and carbon 2, these 2 guys form another sigma bond. And on top of that, what do I have? 2 pi bonds. Okay, so in this carbon you have 2 more atomic orbitals. Let's make them blue. And then this guy have 2 more atomic orbitals. Okay, now my pi bonds, I have a carbon, carbon, H, H. And that is an sp, and that is an sp, and that is an sp, and that is an sp. So that's an sp of this carbon 2, and this is an sp of this carbon 2. That one and that one. That is an S of hydrogen and an sp of this carbon. That is an sp of this carbon and an S of hydrogen. But each one of these carbons have an atomic P and another atomic P. And these are 90 degrees like they always have been. And this has 1 electron, and so does this one. And this was 1 electron, and so does this one. So this right here is 1 pi bond. And this right here is another pi bond, and I will show you the model. This is my carbon, and this is my carbon. This is my hydrogen, and this is my hydrogen. This represents the sp of carbon with a S of hydrogen. sp of carbon with a S of hydrogen. This, between the 2 carbons, is a what? sp, sp, sigma, 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 sigma. So sigma is a strong head-to-head collision. sp on top of the other sp. Now this is my atomic P of 1 carbon and my second atomic P. My atomic P and my second atomic P in the blue. And they overlap side to side. So I have 1 electron here left of carbon 1 and 1 electron here left of carbon 2. And they go very labile, very weak pi bond. And then the other p orbitals, 90 degrees. Okay, so I have a huge electron density. And when you take organic chemistry, all this are going to have like 50 layers thrown on top of it. Why is the reactivity of acetylene what it is? Because of these triple bonds and the single and double bonds. So one of them is a pi bond, and the other one's another pi bond. Okay, so when you have this is a pi, and that's another pi. That's a sigma, and that's another sigma. And that's a pi px with a px, or whatever. Py, you can call them p whatever. It doesn't matter. Pz and pz. But they're atomic. They didn't hybridize. They're not a new orbital. Okay, and in the book, it's a little bit crazy looking, because these drawings are not awesome. You really need models to see them. Now let me say something that I need to add that comes all the way from Lewis from a couple modules ago. Let me add, because now it will make sense. Bond length and bond energy. In certain compounds you have, like in C2H6 versus C2H4 versus C2H2. Certain compounds we have single bonds, certain compounds we have double bonds, certain bonds you have triple bonds, right? And I am zooming through Lewis. Let's assume, since we've talked about Lewis for, I don't know, 3 weeks now, at least, we can do Lewis of all this. C2H6, carbon bonded to carbon, HHH. This is how fast Lewis you can do after you know what you're doing. Okay, so first you start and you have to snap and you have to do this and that. And after a while it's like, I can do this with my eyes closed. That's when you're ready for your test. That's C2H6. C2H4, we just did a minute ago. C2H4. And C2H2 I just finished doing. This is acetylene. This is what the torches have. The gas that is very flammable. We use for torches. So we have, what kind of bond? I want to know about that bond. I want to know about that bond. And I want to know about that bond. And I want to know about what type of bond. I want to know about the energy of that bond. And I want to know about the length of that bond. What do you think? If you have A, okay, so this is ABC. This one is ethane. This one is ethene, and this is acetylene or ethyne. If you have A versus V versus C, and I ask you, what kind of bond is between carbon-carbon? What do you think is that? That's a central atom. This is the kind of question that your test has. Because you don't have to, you just do the hybridization once. And once you learn that, all you need to do is count. And what do you have here? This carbon has a count of 4. So what kind of bond is that one? For a count of 4, what was the count of 4? sp3. Why sp3? Because I need 4. One of the S and all 3 of the B's. Okay, so we did it already. We already learned it. And we go straight. Count of 4, sp3. Count of 3, what? sp2. Count of 2, sp. Like that. Okay? So that bond in A, that is an sp3 of one carbon overlapping with a sp3 of the other carbon. If I only have single bonds, those are all sigma. What about this carbon right here? Overlapping with that one. What is that? A count of 1, 2, 3. So it's an sp2 of this carbon and an sp2 of this other carbon. Are we okay there? Any questions there? And the other bond is a what? A pi. A py with another py. Or a pz with another pz, whichever one you want to call it. A py with a py. Atomic, not hybrid. What about in C? I have a sigma bond, and in this sigma I have a count of 2, so it's a what? sp overlapping with an sp. And the other, that's a pi, and the other one is another pi. And that's a pz with a pz. Going towards you, towards the auditorium and towards the screen, side to side with 1 electron in each. From the ceiling to the floor, 1 electron in each, side to side. Okay, so a side to side collision and a car collision is not as energetically horrible as a head to head collision. Now, bond length. If you have a triple bond and you have 3 bonds, that bond is going to be so much closer to the neighbor than if you have a double bond. Or if you have, I even made it longer here. Okay, so you have an sp, but in here you have a concentration of energy. So that's going to be shorter than that one. But that one is the shortest. Shortest of all 3. You have a triple bond. So if you're going to break a triple bond, and that's so little, and it's so tiny, is it going to require the same energy that if you're breaking a very long labile? No. This is going to have the lowest bond energy. The easiest to break. Much easier than if you have to bring a double. And this would be the shortest bond length and the highest in energy. Okay, so these concepts of bond length and energy were started all the way from Lewis, but it just repeated. And any questions in module 12? There's a very interesting molecule in page 12-10 that I want you to do as homework. Do every bonding in here. CH, C2 has a double bond, C3 has a double bond O, C5, HHH. Draw every single bond as far as single, sigma, and all of these for homework. Have a great day. See you next time.